Okay, so we can see a lot of different examples of oxidation reduction reactions or redox reactions, which transfer electrons from one element to another, which results in differences in the charges of atoms as you go across the equation. And so that's going to be due to the transfer of the electrons in the process. So overall, oxidation reduction reactions or redox reactions are processes which involve the transfer of electrons between two reaction partners. So these can be atoms, molecules, or ions, and they result in these particles having different charges at the end of the equation. So on one side, the charge on a molecule will be different than it will be on the other side of the equation. So now we're going to take a look at a couple examples of redox reactions. So we said our battery cell is a good example of a redox reaction. And we also can see that corrosion or rusting, the deterioration of metal by oxidation, is a good example of a redox reaction going on. So in fact, this is a very important type of redox reaction because there are huge economic consequences of rusting. So it's been estimated that up to 1/4 of the iron that's produced in the United States is used to replace bridges, buildings, and other structural supports that have been destroyed by this rusting or corrosion process. So we'll take a look at some examples here when we do our tutorial on recognizing redox reactions in a little bit more detail. We'll take a look at this corrosion process, maybe using iron as an example. So combustion is another good example of redox reactions going on. So this involves the burning of a fuel by rapid oxidation with the oxygen that's in the air. So again, you'll see that a lot of the processes that are causing redox reactions or resulting in redox reactions involve the use of oxygen, which is why it is utilized in the nomenclature. It's because oxygen is so plentiful on the planet and lots of things are reactive with oxygen, and it often causes this transfer of electrons in the process due to the electronegativity of the oxygen molecule. So we can have combustion reactions that will use organic materials, so things like gasoline, fuel oil, natural gas, wood, paper, and us. Well, we don't actually burn in the air, but we actually will burn sugars and things like that to do our own metabolism. These are examples of combustion reactions or things that utilize oxygen. So we certainly utilize oxygen. We're constantly breathing it in and out. We're actually using it for combustion processes inside our bodies. Some metals will also burn in air. So we'll see an example of this in class. And you won't actually be able to look at it directly because it's very, very bright. But if any of you have ever used a magnesium fire starter, you know you can flake off magnesium and it burns really, really well. So if it just catches a spark, it'll catch on fire and you can use this to start a fire. So we can use an example of our hydrocarbons during a combustion reaction. So this would be something like gasoline that might be burning. So hydrocarbons are things that have hydrogen and carbon associated with them. So our gas molecules are very long hydrocarbons. So we're going to see as we go along in the class that carbon-hydrogen bonds contain a tremendous amount of energy. And if we can oxidize these and cause an oxidized product like carbon dioxide to be produced, the carbon-oxygen bonds have a lot less energy than the carbon-hydrogen bonds. And when we break those, we can lead to the release of significant amounts of energy. So that's why when we burn our gasoline in our gasoline tanks, they undergo this combustion reaction with oxygen, and they're forming CO2 in the process and water, plus a huge amount of energy. So either the energy is going to be released and be used for work. It could also, if it goes very, very quickly, it could be released in the form of fire or an explosion. And it can also generate heat to be releasing that energy. So that's why the engines in our cars get very hot when they're running. The energy that they're producing by breaking down the gasoline actually will create heat and generate significant amounts of heat. So all of the energy is not efficiently converted to the movement of our vehicles. A lot of it becomes lost as this heat. So we have an example, methane gas, for example, can be used as an energy source. In fact, we know this is a byproduct of the decomposition of organic molecules oftentimes, and this happens in our landfill that is in between Corvallis and Monmouth. If you've ever driven down there, you've probably seen the Coffin Butte landfill. So if you've noticed, sometimes you can see flames kind of shooting off from that facility. That facility is actually equipped with a methane harvesting apparatus. And so as the dump actually emits methane, the dump is actually trapping that methane and it's utilizing it to create energy. So we're actually getting energy back from the materials that are ending up in the landfill, which is really great. Sometimes they have too high a production. They don't have enough place to store the energy that gets created to send it back to the power plants. And so sometimes they have to actually burn off that gas. And so sometimes you'll see the methane tower actually burning off the methane gas at the dump site. So that's what that flame is by the Coffin Butte dump if you've actually gone by there. So methane, if it combines with oxygen, it's going to get fully oxidized to the carbon dioxide. So all of the hydrogens are ripped off and all of the electrons that are associated with the hydrogens are also ripped off, and they're donated to the oxygen molecule to form water. So the carbon is losing these electrons, so this is the oxidized component, and the oxygen is gaining the electrons and the protons, and it is going to be the reduced component. So oxygen is acting as the oxidizing agent. It is going to oxidize the carbon molecule, and it itself is being reduced. So the carbon is acting as the reducing agent. The methane is acting as the reducing agent. It's going to end up reducing the oxygen gas to water, and in that process, it itself becomes oxidized. So we'll take a closer look at this as well when we do our review of the redox section. So we'll do a lot of paperwork on this too. So we said respiration, or our process of breathing, is also a redox reaction. So we're actually using it for the combustion of sugars inside our bodies. The redox reactions help to provide the energy that all living organisms need. So our energy is released from the food molecules, and in fact it's released mainly from the carbon-hydrogen bonds again. So things like lipids or fats have a lot of carbon-hydrogen bonds to them, and so they're really energy rich. So lipids or fats typically will give 9 calories per gram of fat, whereas carbohydrates and proteins have fewer carbon-hydrogen bonds in comparison. They still have a lot, and they're very useful, but they have less than the lipid or the fat structures. And so they have less caloric intake value when we're thinking about them. So proteins and carbohydrates are worth 4 calories per gram. So again, be thinking that chemistry is a great way to hold energy. Another process that involves redox reactions is bleaching. So this makes use of the redox reactions to help decolorize or lighten colored material. So examples would be bleaching your hair to turn it blonde, or bleaching your clothes to remove stains, or bleaching wood pulp to make paper. So different oxidizing agents are used for different situations depending on what you're doing. So commonly hydrogen peroxide is a good oxidizing agent that's used for hair to make the hair blonde. Sodium hypochlorite or bleach is used for clothes, and elemental chlorine is often used for wood pulp to create paper. In all the cases above, the colored organic material becomes destroyed by its reaction with the strong oxidizing agent. Metallurgy is also another example of redox reactions. So this would be the science of extracting and purifying metals from their ores, and it makes use of numerous redox processes. So worldwide, there's approximately 800 million tons of iron that's produced each year, and it's produced by the reduction of the mineral hematite with carbon monoxide. So you can see the structure for the hematite down here. There's lots of oxygen. So what they're doing is they're isolating and purifying the iron away from this compound. And to do that, they have to do a redox reaction. They have to reduce the iron. So if we look at iron oxide, we can tell what charge state it's in, right? So we've got oxygen, which we know is -2. There's 3 of these guys present, so it's -6 total. We've got 2 irons here, so it's got to balance and have a +6 charge, so the iron in this one must be +3 in its charge state. So if we look over here, we've got elemental iron on this side, so we know what about the charge state when we have elemental forms of our elements. It's going to be 0, right? So we've gone from being a +3 state to 0 charge state. So to become less positive or more negative, you've got to gain electrons. And so it means that the iron from this side to this side is being reduced. It's gaining electrons. So it is the GR part of the equation. If you gain electrons, you're reduced. So that means something else has to give those electrons or lose electrons and become oxidized. So this guy must be losing the electrons and becoming more oxidized. And you can see that it's gaining another oxygen. This one's losing those oxygens. And so our carbon monoxide is actually being converted to carbon dioxide, and it is being reduced. So we don't typically think of carbon as having a charge state, but what it does have is, or what we can give it, is an oxidation number. So we know that when oxygen decides to take its charge state, it's always -2. And so we can say the oxygen, being more electronegative than the carbon, is hogging those electrons most of the time. So this carbon actually appears sort of positive, right? It's got a delta positive on it. It's a polar covalent bond. And so we can assign it an oxidation number. So in this case, if we say oxygen takes on a -2 oxidation state, the carbon then must be +2, because there's one carbon and one oxygen. They have to form this neutral molecule. So we can say carbon is the +2 component, oxygen is the -2 component. If we look at carbon dioxide, you can see that now there's 2 molecules of oxygen for every single carbon. So now we've got a -4 charge here. Our carbon is still single, so this must be the +4 side. So this one has gotten more positive from this side to this side. It's gone from being +2 to +4. So it's losing electrons. It's losing those electrons and giving them to the iron. So how do you recognize redox reactions then? You recognize redox reactions by determining if the elements or ions that are involved in the reactions have a change in their charge. And so we'll give you some clues as to figuring out if you've got a redox reaction and how you can actually evaluate this. So if you've got a reaction that involves metals and nonmetals, you might predict that you gain or lose electrons. And so molecular substances can be analyzed in terms of loss or gain of oxygen, or by extending the ideas of oxidation and reduction to increase or decrease the electron sharing. And so this is going to involve the electronegativity differences to try to evaluate this. So an atom is oxidized when it loses a share in the electrons, and an atom is reduced when it gains a share in the electrons. So what does this all mean? So how can we boil this down a little bit? We actually have a formal system that's been devised for helping us keep track of changes in electron sharing. And this will help determine then whether atoms are oxidized or reduced in the reaction. This is a value that's called the oxidation number, or oxidation state. And so this is used in evaluating the covalent bonds, since they don't normally take a full charge state. So we evaluated the oxidation number of the carbon in the last reaction that we just took a look at, with this reaction of the hematite to purify pure iron from this compound. We said that the iron is becoming reduced and the carbon is becoming oxidized. It's the one that's losing those electrons. And so we did that by assigning an oxidation number to the carbon based on its role or its bonding with the oxygen atoms in either carbon monoxide on the left side of the equation or the carbon dioxide on the right side of the equation. So if we compare the oxidation numbers then across the equation for each atom before and after the reaction, we can tell if the atom has either gained or lost shares in the electron capacity. So oxidation numbers do not necessarily imply ionic charges. So they're simply a convenient device for helping keep track of the electrons in redox reactions. So when carbon and oxygen bond together, they're still sharing the electrons. The carbon is not positively charged and it does not form an ion, and it will not dissociate if you put it in a solution of water. The carbon will stay with the oxygens in its bond for carbon dioxide. So we do have some rules to learn for assigning oxidation numbers, and these are pretty straightforward. If you have an atom in its elemental state, it has an oxidation number of 0. So if you've got a metal like sodium or magnesium or iron, if it is just in its solid state, the oxidation number for that, or the charge on that, is going to be 0. And so you've already heard that all of our elements kind of start off as being neutral in their charge state. They only change this if they lose or gain electrons. This is also true for our diatomic molecules that occur as natural elements in the periodic table. So this would include things like O2, Cl2 gas, H2 gas, nitrogen gas. All of these things are H2, N2, O2, Cl2. These are the naturally occurring ways that these elements occur on the planet. And so these are also neutral in their charge, so their charge state is still 0. So anything in its elemental state has an oxidation number of 0. Our monoatomic ion has an oxidation number equal to its charge. So if we have a calcium ion, the oxidation number would be equal to 2+. If we have a molecular compound or a covalent compound, an atom usually has the same oxidation number that it would have if it were a monoatomic ion. The only time that's going to differ is when you have things that are dramatically different in their polarity. So if you have, say in our example of carbon, when it's bonded to oxygen, it can alter its oxidation state to accommodate the oxygen molecule. And that's because it can form double bonds or triple bonds with the oxygen molecule to fill up its valence electron shell. But when it does this, it doesn't share equally with the oxygen, and so it takes on this partial positive charge to it. And we can evaluate that with this type of oxidation number. So if we take some examples that are down here, we can look and evaluate our charge state. So we know that hydrogen and chlorine can come together, and we would give the chlorine is the more electronegative component, so we'd assign it at -1, and then we assign the other molecule that's coming off of it as equal and opposite in charge. So if this one is -1, this one's got to be +1, because again, this compound has to equal 0 when you make a neutral compound. So a water molecule is going to share 2 bonds, because the oxygen likes to share 2. Hydrogen likes to share 1, and so the oxygen in the oxidation numbering scheme is going to get the -2 designation. So the more electronegative atom, in this case that's oxygen, is going to get the priority for the oxidation number. The partially positive partner has to take on whatever oxidation state is needed to make that molecule neutral when you come out on the other end. So for example, when we're looking at our water molecule, the water is the most electronegative, and so it gets its preferred charge of -2. And then the hydrogens have to counterbalance this, and since there's 2 of them, each of them is worth a +1, which is its common ionic state as well. So we can see 2 + 1s -2 is going to equal 0, and we've got a nice neutral compound. Ammonia, the same way. The nitrogen is more electronegative than the hydrogens, and so it's going to get its preferred charge state of -3. The hydrogens on the outside are each worth +1, and so you get +3 -3 is going to be 0. So the net overall charge on our molecule is going to be 0, just like we saw for the ionic bonding. And so we'll get a little bit more practice with our oxidation numbers and recognizing redox reactions in a review tutorial that we'll do. So we'll stop here for now.